I'd like to inform you about the current situation of our schedule today. There's a small change in the part of our program. Instead of Mr. Cemil Koyunoğlu, our speaker from the second day, Miss Dila Hocaoğlu, will be on the stage. Dila Hocaoğlu will talk about integrated wastewater management for sustainable agricultural operation using Spirulina. Please note that her presentation title is a little bit different from the main focus on our session 3. But Cemil Koyuncuoğlu will be here tomorrow, and I'd like to invite my dear friend to the stage with the title of Integrated Wastewater Management with Spirulina. The floor is yours.
Hello everyone, my name is Dila and I will talk about my thesis research that's named Integrated Wastewater Management for Sustainable Agriculture Operations using Spirulina. First of all, I will talk about, I will mention the project and, sorry, but it's not working, I guess. Anyway, so let me first talk about the project overview and the purpose of the project. I guess it's not being seen properly on the screen. Right. Tamam. Şunu nasıl düzeltebilirim? Ya da böyle mi devam edeyim? Sanırım oldu. It's okay right now, I guess. Yeah. First, I will talk about the project overview and the purpose of the project. So, my research belonged to a bigger project that's designed to suggest a circular, sustainable farm operation system. And the main idea behind the project is to collect the wastewater in the microphone. So main idea of the project is to collect the wastewater. The bigger project's main idea is to collect the wastewater and then separate it into two and direct the sludge portion to an anaerobic digester and the liquid portion to an algae photobioreactor that will be placed upon a water body that will be nearby the farm. Resulting biomass could be used for many purposes, and in my case, depending on the farm needs, but in my case, we evaluated the potential for fertilization applications, and the effluent treated wastewater could be used for, again, depending on the farm needs, for many purposes, like irrigational purposes, cleaning purposes. The effluent quality is important at this point. So my study consisted of two phases. The first portion was the pretreatment by chitosan solution and then phycoremediation, the pretreated wastewater. Sesimi açmam isteniyor ama bunu kabul mü etmeliyim? So, on these pictures, you see the farm that I collected my wastewater. They have around like 300 cows. They operate, they have around 300 cows. They are dairy production farm. They operate organically. They don't buy any feed from outside. They grow their own feed for animals. They don't use any fertilizer. They use their, the animals' manure as fertilization applications. And they don't use any drugs or supplements unless the animals are sick. They also have this, sorry, no. So they also have their own wastewater collection system, a primary separator system. In this second picture, you see a concrete pit that they collect their wastewater into this pit. And once enough solids are accumulated in the pit, they direct the wastewater into this separator. And after the separation, the pre-treated solid separated effluent is redirected into this pit again. And this is right where the collection was done, right after the separation was done. So the first thing that I did was the characterization of the wastewater, and then I needed to decide the optimum amount of chitosan solution to be able to determine the minimum amount of chitosan solution for maximum amount of solids removal and microbial community removal. So that amount was 20 milliliters per 50 milliliters of wastewater, and scaling up was done accordingly. And in these pictures, you can see some portions of that study. And this one shows jar test, a portion of the jar test, and in the middle one you can see portioned raw wastewater. And this one shows the pre-treated wastewater. It's clean and non-turbid, so ready to use in further experiments. And then the next thing that I did was to conduct a multi-well plate assay. I did that to be able to determine the optimum amount of inoculation, optimum amount of culture needed to inoculate the wastewater. So the amounts that I tried was 1/10 of the final volume of the culture, 2/10, 3/10, and 4/10. 4/10 was the most successful one, so the further experiment was done using the 4/10 ratio. And in this slide, you can see the inoculation, the experiments that was done in custom-made plastic PBRs. I designed these plastic PBRs out of irrigational hoses. They are easy to find. They are cheap. They are readily available. They are elastic, which is an important quality for if we are planning to place the photobioreactors on top of a water body. So, and also I designed an aluminum skeleton so that I will be able to hang the photobioreactors from above and they will get light from above. And also I will be able to place the culturing portion of the hoses on top of this orbital shaker so that I will be able to mimic the waving motion of the water body. And you can see some pictures of those process. And this is from control study. This is from this is right before the inoculation, and this is right after inoculation of wastewater. And now I will talk about my results. The first table that you see is about the efficiency of the pretreatment process of chitosan. The raw wastewater had almost 1,400 milligrams of nitrogen species, and after the pretreatment, it was reduced almost to 2 milligrams per liter. That sums up to 85% removal by chitosan solution. For phosphorus, it was 250 almost, and was reduced to almost 70 milligrams per liter. That sums up to almost 93% removal by chitosan solution. And for COD, it was 37 grams per liter in the pretreated, raw wastewater, and it was reduced to 13 grams per liter, and it sums up to almost 65% removal by chitosan solution. And what this means for us, the usual medium that we use in the laboratory to cultivate the Spirulina species is Spir medium, and it has almost 400 milligrams per liter nitrogen species and 80 milligrams per liter phosphorus species. That means that we have remaining half of the nitrogen species that the species is used to grow in, and also the phosphorus species is almost 1/4 of the usual amount. So it's really nutrient limited medium for the species. On this slide, we see the multi-well plate growth results, and like I said, the most successful one, the 4/10 inoculation ratio was the most successful one for wastewater. So the further experiments was done using this ratio. So these graphs, four graphs, compare the growths of species in plastic PBRs for control and wastewater studies. The first graph shows the filaments versus time. We see blue ones depict the control PBR and orange ones depict the wastewater PBR. We see the straight line for filaments number. That means that the filaments number did not increase over time, which was something expected actually because the nitrogen amount, phosphorus amount, pH was as it was expected. It was the same as the control studies, and dry weight was also increased when we look at the control study in the wastewater study. These two graphs show the nutrient removal profiles of the cyanobacteria species. So, what we can clearly see, immediately see, is that the species, nitrogen and phosphorus species, were immediately taken up in the first couple of days of the cultivation. For phosphorus, it was almost 80% removal, and for nitrogen, it was almost 60% in the first 2 days, and 10% in the next 2 days. So, it was pretty fast removal. And on this table, we see overall efficiency of the effluent, we see the overall efficiency of the treatment process. So we talked about the chitosan removal process, and when we look at the phycoremediation portion, the cyanobacteria was able to remove almost 15% of the nitrogen species. That sums up to almost 100% when coupled with chitosan pre-treatment. And for phosphorus species, it was 5.5% with phycoremediation. That sums up to 98%. For COD removal, it was almost 30% by phycoremediation. That sums up to 93%. And for solids, we see this gap because after pre-treatment process, I wasn't able to measure any kind of solids remaining in the wastewater because it was, as you have seen, it was pretty clear, so I wasn't able to measure with the equipments I had. So after the phycoremediation portion, however, I was able to detect some solids, so that sums up to almost 93% again, overall removal efficiency. And now I will talk about the biomass analysis. The first analysis I will talk about is the nutritional profile of the biomass. So these graphs show the total protein, total carbohydrate, total lipids. When we look at the proteins, we see almost 73% of protein production in the control group, whereas we see almost 42% protein production. These are something we also expected because when the nutrients, nitrogen and phosphorus species was not that high, so the cyanobacteria species was not able to produce that much of proteins. And when we look at the carbohydrates amounts, it was almost 40% for control group, and it was almost 27% for wastewater group. And when we look at the lipids, we see a doubled production of lipids when we compare it to the control group, which is also something expected because when the nutrients are scarce, we expect the lipids, we expect the species to accumulate lipids. So that was something expected. And when we look at next, these are the results from fatty acid composition analysis. The first row shows the control PBR results, and the second row shows the wastewater group. When we look at the table, we immediately see that the types of different FAME profiles were decreased when compared to control PBR. The biomass that was grown in the wastewater wasn't able to produce these 3 FAME profiles. And this is something actually somewhat unexpected because we saw an increased amount of lipids production in the wastewater grown biomass, but this results does not really correlate with that. You might not have been able to determine the stored lipids in with our analysis methods. And this table shows the vitamin B content of the harvested biomass. Again, we can clearly see that some of the vitamins that the biomass grown in the control PBR wasn't able to produce, were able to produce by the biomass that was grown in the wastewater. And what we also can see is that their production are increased, and some of them are 6-fold for thiamine, for example. And it was 2-fold for B3, nicotinic acid, and it was 4-fold for pantotenic acid B5. This suggests that the wastewater cultivation, the biomass cultivated in the wastewater was able to produce these and wastewater promoted their production. This is a little bit of crowded table, but it shows the elemental content of the biomasses. The first thing that we noticed was the macro and micronutrients were they were lower than the control group. But for example, magnesium, potassium, aluminum, manganese, iron, they were all in lower amounts. And also what we were able to see, that the biomass that was grown in the wastewater accumulated some of the heavy metals higher than the control PBR. This is something that needs to be investigated further because we don't really know the source of the heavy metals. They could be the water that they use in the farm, the soil type, the soil content of the farm. That needs further investigation to be able to conclude what the source is for these heavy metals. And this is again a little bit of crowded table, but it shows the amino acid content, amino acid comparison of the biomasses. On this table, we see some of the amino acids were produced higher amounts in the control group, whereas some of them were higher in the wastewater group. So we don't really have a straightforward conclusion from this study, but what we were able to see was the ones that were higher in the wastewater biomass were greatly increased. For example, it was 2-fold for arginine, and it was 3-fold for histidine. It was 7-fold, 7 times higher for isoleucine and leucine. Lysine was 2-folds, methionine was 9.5-folds, phenylalanine was 17.5-folds. Tryptophan wasn't produced by the control group, whereas it was produced by the wastewater group, and tyrosine was 4-folds, and valine was 16-folds. This table also shows us some interesting findings, and these three amino acids are the ones that are precursors of some biostimulants that encouraged us to investigate the biostimulant presence in the biomass. So we continued with that, but we did a qualitative analysis so that we will be able to see the presence of them. So we determined these 23 classes of compounds, biostimulant and phytohormones, and we determined these by looking at the methodological availability and the applicability by our instruments. And we were able to see 4 of these compounds in our biomass that was grown in the wastewater. Two from the jasmonic acid classes, 1 from gibberellins, and one aminocyclopropane, 1 carboxylic acid, which is the immediate precursor of ethylene. And this compound's immediate precursor is methionine that was produced almost 10-folds in the wastewater biomass, so this is a promising result for us. So to conclude, what we can say is that when coupled with chitosan solution, chitosan pretreatment, the overall treatment process was able to remove almost 100% of the nitrogen species, 98% of the phosphorus species, and almost 23% for COD and solids. The system was able to remove. We were also able to see the biomass that was grown in wastewater was able to produce more vitamin Bs than the control group. We were able to see some interesting results for amino acids production in the wastewater group that the control group was not able to produce in that amount. And also we were able to see some biostimulant presence in the wastewater biomass that would suggest their use as biofertilizer. Of course, the optimization further needed and quantification is needed. So I think that was some of my presentation. Thank you very much for your attention.
Thank you very much for your nice presentation and for your nice closing. If you want to ask any question, you can ask right now. We can continue with your questions. Yes, please. Yeah, it's coming.
Well, thank you for the presentation.
Yeah.
I just wonder, I think, if I'm not mistaken, that was a batch-wise study. So you have
Yeah.
tried it only once, not anymore, right?
I mean, yeah, these are
So
these
there was
results are
no
from only one
continuous
study.
feeding at all?
Sorry?
No continuous feeding, right?
No.
So what was the initial mixture ratio of your feed from the wastewater? So you have this growing media, let's say 10 liters or something?
Oh,
and
no,
how-
that wasn't any dilution in the wastewater because the limited nutrients were pretty limited in the wastewater, so we didn't do any dilutions.
What I'm trying to say is that, you know, how many liters of digestate or the liquid part you fed into that?
Oh, it's
growing
2
media?
liters per bioreactor.
And what was the volume of the bioreactors each?
2.
2. So
Yeah.
1 to 1. Okay. Almost.
You mean the dilution 1-to-1? No, we did not do any dilutions with the
Okay,
wastewater.
so-
It was all the wastewater
I
itself.
see. Okay.
Yeah.
So I haven't seen the oxygenation levels over there. What was the anaerobic conditions
We
during these experiments?
We did not do any anaerobic studies with this study, I guess.
No. What I'm trying to say, you have a lot of significant amount of organic materials inside the growing
Yeah.
media. So normally you should expect some anaerobic conditions over there. So I wonder
Unfortunately,
if you have
yeah.
any experience like that.
I guess I'm not really understanding the
Okay,
question.
then.
That's why I'm
All
not
right.
able to answer.
It's all the time. So you're just sweeping the air outside. Okay. All right. Okay. Then. Thank you.
I'm sorry.
Congratulations.
I think that's all.
Yeah.
Thank you again for your nice presentation.